hi class. So I'm gonna cover today electrodes and an introduction to bioinstrumentation. So the last time we talked, we were talking about ECGs and EMGs and EEGs. Now I want to get into how you actually measure those signals. So now that you know what they are, what kind of instruments do you need to actually perform some measurements? Um, so it's not as simple as just putting metal electrodes onto the skin. You actually have to have special electrodes. And you'll see that when we're measuring voltages on the surface of the skin, there's lots of potential noise and pickup from other external sources. So we have to have a way to basically eliminate that noise from the signal so that you can actually get a clean measurement of what you're trying to measure. Okay, so let's get started. Um, so this is kind of the learning objectives for today. So you're going to learn about electrodes, how they're structured. One important kind of concept is that they are devices that convert ionic currents into electronic currents. And so remember I made the distinction last time that ionic currents are the flow of ions, which are charged particles um, in your body. Remember that we are essentially electrolytes that have many ions in our body. So these electrodes will allow us to convert these ionic currents, which are what make up ECGs and EMGs and EEGs, and convert them to actual electronic currents that you can measure with some circuits. That gets us into kind of what it is broadly labeled as bioinstrumentation. And we'll look at a couple of different types of electrodes and the types of circuitry that you need to basically process those signals. Okay, so here's a quick overview of what bioinstrumentation is. It's basically the use of electronics and biomedical electronics to measure, record, or transmit physiological information. So you've already seen this in the previous lecture where that physiological information is some voltage that's produced by trillions of cells in the form of an ECG. So under that broad category, you can also include any other devices that help you make physiological measurements. So they could be like a small chip that you make that can measure some concentration of some chemicals, which is I guess included in biosensors. It can include pressure transducers. It can include any other kind of physiological sensor that you would see like in an operating room. Um, it also broadly includes things like glucose sensors or imaging systems. And really, this is the topic of ECE 503, which we'll get into much more detail with this kind of stuff in that class. Okay, so let me give you a general, kind of a generic diagram of what a bioinstrument does. Bioinstrument takes a person, you attach some sensors to it. In this case, I mentioned they're electrodes, and you design some system that allows you to do all of these things. So, for instance, when you get the measurement that you want from the sensor, that sensor will then convert that physiological signal to some electronic signal, which can then be processed. So within this little box, you can include like front end circuitry, filters, patient safety circuitry, amplification, etc. The sensor and the electrodes, or I'm sorry, the sensor and the calibration can include like a sensor for chemical sensing, thermal, physical, optical. Once that signal is turned into an electrical signal, you can do some analog to digital conversion to process by like a microprocessor and to also save that data. You can do some signal processing, and then from there you can feed back to any other devices that are connected to the human. Or you can just display it and then transmit that data via some form. So this is, if you're a person working in bioinstrumentation, this is generally what you'll do, but you'll be working specifically on, certain portions of this whole diagram here that you see. So we'll get into that a little bit today, and then the next lecture as well. So bioelectrodes. So these are one form of kind of like sensors. They're not really sensors, but um, they're basically devices that allow you to measure voltages and bioelectric phenomena that we talked about last time. Alright, so let's do a little experiment here on the PowerPoint. So in the simplest case, if you take a metal electrode and you dunk it into electrolytic solution, remember that the electrolytic solution has ions that are floating around. So those are positive and negatively charged ions that are sitting around here. When you put a metal in an electrolyte solution, this is what happens. So I'm going to kind of want to point you to the right here. You have the electrode and you have this line here. This line represents the interface of the metal electrode and the electrolyte solution. When you have the metal there, you're going to have a buildup of positive ions building at the surface of that electrode. So they're going to start sticking to the electrode, and because of that, you're going to get a buildup of electrons on that electrode, on the actual electrode side, the metallic side, just to counteract the positive ions that you're seeing in the electrolyte. So you're going to create this effective charge separation across the interface of the metal and the electrolyte solution. The buildup of, so this is not to scale, so buildup of charges is going to go here, and as you can see, if you were to measure because you have a charge separation, you're going to have some voltage difference across that interface. And it turns out that the electric field is very, very, very strong closest to that interface. So you're going to have a lot of positive charges coming in here, and even some negative charges attracted to this positive here. And there's going to be a effective thickness of ions that are sitting effectively near the metal surface of the electrode. The main important kind of part here is to just tell you that because you have electrons on one side of the interface, so on the metal side, and you have ions on the other side, the ions cannot just, break the metal and break the bonds of the metal and then force themselves into the metal. So effectively you have this kind of capacitor looking thing at the interface of this device. So why is it important? Because it creates a voltage difference across the metal and the electrolyte. And depending on the electrolyte and depending on how many ions you have and also on the type of metal you have, that voltage difference can change. And so, for instance, on the right here you have a table that's called half-cell potential. So half-cell potential is what I just mentioned here. It's the voltage that's produced across the interface of the electrode metal and the electrolyte because of a separation of charge. That's called the half-cell potential. So like for instance, if I just highlight aluminum here, if I dunk an aluminum rod into an electrolytic solution, then what this says is that I'm going to get a voltage across that interface that is negative 1.7 volts. That's a really large voltage produced at that interface. So if I were to get my reference electrode or my reference part of the multimeter, put it in the electrolyte, and then attach the other end to the metal, I'm going to get a voltage difference of negative 1.706. Another example is if I get a lead electrode, dunk it in solution again, that will only produce a voltage difference of negative 0.126. Now on the other end of things, if I get a silver electrode and dunk it in electrolytic solution, I'm going to get a positive 0.223 volt voltage difference across the interface. Interestingly enough, if you get a hydrogen electrode and dunk it into water, you're actually going to get 0 volts across the interface here. Okay, so it turns out that we actually use hydrogen electrodes typically as like a reference. So it's our standard electrode, and all of these voltages are in reference to the hydrogen electrode. So what that means is that we can standardize that as being our kind of like our reference. Okay. Um, the other comment I have is that if you put two different metal electrodes into an electrolytic solution, so metal A and metal A will produce a voltage difference from electrolyte to the metal, and then metal B will produce a different voltage based off of that material and that metal. And if you wanted to measure the difference across the metals, then you would just take the difference of these here. Okay, and that leads us to the next uh, uh, slide, which is an example. So let's say that you're given a silver and a zinc electrode, and you submerge them in the same electrolytic solution, and you're asked to calculate the difference between the two electrodes. So you're going to use this table to help you out. So you say, okay, well, I know that if I put zinc in there, it's going to produce negative 0.763 volts. If I put silver, I'm going to get plus 0.799. So you just basically get the difference, and you see that you have a difference of 1.562 volts that you'll measure between the silver and the zinc. Now I bring this up because of this question here. So is a voltage difference a good thing if you're trying to measure a bioelectric signal? And really the answer, to kind of hold, not to keep you in suspense, is no. Think about it this way. When you use these electrodes or these metals, you're already imposing an artificial voltage signal just from the half-cell potential. So if you have a ECG signal that's on the order of, say 50 microvolts, that's going to be superimposed on a voltage that's 1.5 volts. So you're going to have what's called a dynamic range problem, and what that means is that you're going to have the problem of trying to measure a microvolt signal on top of a signal that's a million times bigger. So it'll be very hard to basically measure that. And so the take-home message for this is that you want to eliminate these voltage differences across different electrodes. One way of doing that is to use the same electrode, right? Because hypothetically, if I use two silver electrodes, they would both produce a 0.799 volt difference. So then technically the difference of both of those electrodes would be zero. But actually that's not the case. Even if you have two of the same electrodes, you're still going to have some residual voltage. And so it turns out that we've studied different electrodes and have found that these specific electrode types in this table here, when you use the same electrodes in the same solution, they will produce a very small voltage difference, but we're on the order of now millivolts instead of volts. So you can use stainless steel electrodes, and in fact these are mainly used for like measuring EMGs invasively. And you see that if you put two stainless steel electrodes in saline, which is basically an electrolyte, you'll get a 10 millivolt difference between those two stainless steel electrodes, which is very small compared to what you were getting earlier. If you put two silver electrodes, you won't get 0, you will get 94 millivolts. And there's other ones called silver chloride electrodes. Alright, so I highlighted silver chloride for this reason. The first reason being that you see that the difference between electrodes is actually very small. So what does this mean? You have one silver electrode and one silver chloride electrode, and that produces a 2.5 millivolt difference, which is very, very small. And if you use a sponge, you can even get much smaller voltages. So how does a silver chloride electrode work? So let's go down here. This is the better picture here. So on one end, so this is supposed to be submerged. I should have drawn this. This is supposed to be submerged in electrolytic solution like saline. So let's say that you're submerging this in electrolyte. On one end, you have silver. On the other end, you have silver chloride. Okay? So let's click on this end over here. So if you have silver on this side, let's say somehow you knock off an electron from that silver and you are allowed to flow in a closed loop back to the other electrode. As that electron zips by, because you're applying a potential difference, that electron then combines with the silver chloride on this electrode here. When silver chloride, AgCl, combines with the electron, it's gonna essentially separate the chlorine and the silver. So the electron will go to the chlorine, and what you'll have is silver molecules and chlorine molecules are now dispersed in the electrolytic solution. So with that, the chlorine, because there's a deficiency in electrons over here, the chlorine will zip back to the other silver electrode, and that chlorine will then interact with the silver on the edge here, and when they combine to be silver chloride. But because they combine to be silver chloride, which is the solid, it releases the electron, and then that goes back into the circuit and goes back into the loop here. And so what I kind of want you to take away from this is that on the electronic side, where you have a voltage and you have these wires, you have the movement of electrons. And once they interface with these electrodes, that electronic current converts into an ionic current, and that ionic current is the movement of chlorine. So you can see that the movement of chlorine is equivalent to the movement of electrons, and you're able to basically convert from one to the other. And that's a powerful thing, because remember that we are like electrolytic solutions. So we have chlorine in our bodies, we have chlorine in our sweat, we have chlorine in other biological fluids. So if you have a flow of chlorine atoms, you can then use silver chloride electrodes to convert that to electrons. And that's how it does it. So I want you to memorize this and know how this works. That essentially silver chloride is just like on the surface of these electrodes, and when it combines with an electron, it produces just silver ions and chlorine ions, and then the chlorine ions combine on the other end to the other electrodes to release the electrons and flow back in a circle like this. Okay, so this is what it looks like down here. So this is what a typical ECG electrode looks like, and even an EMG electrode. Let's go from the bottom here. So this is the skin, that's the interface. This is effectively like your electrolytic solution. There's a little chamber inside that has a sponge that's also filled with electrolyte, and that's going to allow you to have like silver and chloride kind of like, you know, dissolved into this little solution. Then you're going to have another electrolyte here, and really what we're getting to is that we're finally going to get the silver chloride conductor here, and there's an electronic snap that can connect to circuitry that's outside here. So this is the interface where you can convert ionic currents like silver and chlorine into electronic currents on this end here. And so you just have a couple of mechanical structures here that are to basically attach and adhere to your skin, but effectively you're creating like this interface between metal and chlorine or silver chloride and your skin. So that's how you're able to actually measure an ECG signal. And remember that we're using silver chloride, so you know, when you're measuring the voltage differences between like the left arm and the right arm for the ECG, you're only going to have 2.5 millivolts of noise, which is great in terms of minimizing the amount of noise that's in your signal. Okay, so as you can kind of tell, this creates a very complicated interface on your skin, And if you're an instrumentation like engineer trying to figure out how to actually process these signals, you have to understand how exactly the electrodes are interfacing and basically what the impedances look like at the skin. So here's what it looks like. So if you take one like electrode A and you attach it to skin, it's gonna look like this, where essentially you have a voltage which is from the half cell potential from that specific electrode, and then you're gonna have some associated capacitance and resistance which is associated with that double layer. Remember that's the separation of the ions and the electrons in the metal electrolyte interface. And then you're going to have like a lump resistance associated with your skin. So in total, this kind of like what's in the box here would constitute what the impedance of the interface of the electrode and your skin would look like. So again, if you're designing instrumentation that interfaces with these electrodes, and you wanted to model what that interface looks like, it would look something like this. And you have to kind of consider that when you're designing everything on the right of here. Okay. This is for electrode B. That's the same kind of thing. We'll get to this differential amplifier here in a second. All right. A more, I guess, accurate way of modeling the interface. There's two ways. There's called the Warburg electrolyte impedance, where you have just two elements, the polarization resistance and the polarization capacitance. These are both frequency dependent, so the values are dependent on the frequency that you're operating in. But more accurately, you're going to use the one down here, where you have some resistance capacitance, half cell potential, and you even have some leak resistance for the passage of DC current. So we would use this impedance here to basically model the impedance of an electrode skin interface. And the values of these will depend, but they're available, just basically researching these values online. Okay, so I want to get now into some of the types of electrodes you'll see. So a lot of these do have silver chloride as their electrodes, but if they don't, I will mention when they don't. So the first type you'll see are strap electrodes, and this is just designating essentially how they're attached to your skin. So the way these work is that you have a wire, you have some binding post, and then the electrode surface. So that's strap electrodes. You'll have some strap that's going around like your wrist or wherever you're connecting it. You'll have suction electrodes, so you'll have some suction kind of mechanism, and within that you'll also have the electrode interface. So then you just would press this down or suck on the rubber ball, and it would basically create a suction on your skin. This is if you really need some really good interfacing between the electrode and the skin. You also have column electrodes, which are the most common for ECGs. So you'll have the gel-filled electrolytic solution in here adhering to your skin. You'll have some adhesive here, like tape or something, and then you'll have silver chloride on the azure metal, and some button contact, which basically just interfaces with some wires. What are some problems with some of these surface electrodes? So obviously poor adhesion. So the interface between this electrolyte and your skin is very important. If there's any air in there, you don't have a proper transfer of ionic currents from your skin to that gel-filled chamber. You also have movement artifacts. So whenever you move, if you move this electrode, that'll register as a voltage reading. So that's another problem. And the last problem is with erosion. So because you have a metal here interfacing with a liquid, you will get some corrosion and erosion on the surface of that electrode, and that'll manifest itself in terms of a poor reading, or some junk that's being adhered to on that surface. Here's what ECG electrodes look like. You've seen them before, probably. And the EEGs are more like suction electrodes because the interface from the electrode to the head has to be very, very clean. Okay, so there's also needle type electrodes. These are mainly used for like EMGs. These are relatively invasive, so you actually have to puncture skin and get to the muscle. That means that they are also more accurate in terms of measuring EMG signals. And there's two types. There's bipolar and unipolar. Um, in bipolar, you have a hypodermic needle that punctures the skin. And at the end, you have two little electrodes. And what you do is you measure the voltage difference across those two electrodes to measure the direction and the magnitude of some of the EMG signals you're measuring. You can also have unipolar. So the way this works is that it's only one electrode, and it's a sharp needle, and it's covered by Teflon. But you'd have to measure a voltage difference, so you'd have to have two unipolar electrodes that would essentially you can measure voltage difference across. In this case, the electrodes are not made of silver chloride. They're actually made of stainless steel, and that's because you have to make them mechanically stable because you are puncturing skin. You don't want the electrodes to break, so that's why they're made that way. So they're mechanically stable. They're also cheap, but they're also very noisy. Noisy because if you go back to the previous slide here, you get 10 millivolts of potential difference across two stainless steel electrodes. So that's quite a bit, again, in comparison to like say 0.2 or 2.5. Okay, here is another type of electrode. They're microelectrodes. These are more specialty driven, so what this means is that they're used mainly in the lab, not necessarily in a person. So in this case, if you wanted to do some experiments, say you're a researcher and you wanted to experiment on individual cells, then you can do that by using what are called microelectrodes. They're very small electrodes, and they're made in different ways. But here's an example of how you would use them. So like, again, very simplistic. Say you have a cell, you're going to put it in an electrolytic solution so it doesn't die. And then you would have basically a reference electrode sitting in your electrolyte. And then you would also have a electrode that's very, very small, on the order of a couple of micrometers in diameter, that would puncture the cell membrane if you're trying to measure, like, let's say, a membrane voltage across the cell. So you would puncture the cell, and then you would record a voltage difference across those two electrodes. So in terms of how the microelectrode actually functions, you can have glass metal microelectrodes, and the way these work is that you have tungsten or platinum wire, which is essentially shoved into a glass pipette, and then you have that is then your microelectrode that punctures the actual cell. You could also have a fluid-filled microelectrode, so in this case you have a very small pipette whose opening is about 1 micrometer, and then you have a tapered angle, and within that pipette you have a really small amount of electrolytic solution, and at the end of it you have a silver chloride plug, and that could also puncture your cell as well. So there's two different kinds of electrodes you can use to measure very small organisms. Okay, so just like with standard electrodes, microelectrodes also have their own impedance associated with them. So that's shown here. You can model it as some capacitors and resistors. So let's kind of go over it very quickly. I'm not going to ask you to calculate any of this. It's just for your own reference. So let's say you have you're measuring a voltage from the microelectrode. You're going to have the microelectrode, you still have the same ferritic leakage, so you can have current going back and forth. But you also have a capacitance associated with that double layer that I was talking about earlier. That's from the metal and electrolyte interface. And then you're going to have an additional capacitance associated with the microelectrode itself, because you're going to have now like a glass pipette or glass that is separating the electrolyte. Okay, so if you wanted to measure RS, the spread resistance of the electrode, you can measure it as the resistivity of the electrolyte solution and the radius of the microelectrode tip. For fluid electrodes, so that's here. This is the width of it, or the radius, sorry. For a fluid-filled microelectrode, the resistivity of the electrolyte would matter, and also the taper angle of the microelectrode. Again, I'm not going to ask you to do this, but this is, again, if for some reason you end up in a electrophysiology lab and you're asked to calculate some of these things and how to interface it with instrumentation, these are the equations you can use to do that. You can also measure the capacitance of the microelectrode using this equation here, and again, it depends on the radius of the inside tip, the outside tip, and the dielectric constant of the glass. Okay, I've uploaded 3 videos here. If you're curious about, what kind of work goes into actually measuring like membrane voltages and what kind of instrumentation goes into it, these are some pretty great videos. They're very informal. I mean, this is like I believe this is a grad student who's basically just showing you how to do some microelectrode cell patch clamp work. But it'll give you a feel for the kind of instruments that have to be designed and used to do these kinds of measurements. So just take a look at it. You won't be quizzed on it, but it's good to just see these videos and kind of take in how much instrumentation goes into measuring some pretty simple parameters like voltage. Okay, so what kind of amplifiers do you need? I have some text here, but I'll get to it later. Let's get to what you need. So recall that when you have 2 electrodes, you're going to have a voltage difference across them, even if they're the same electrodes. And that voltage difference is gonna basically be noise that is sitting on top of the signal that you want to actually measure. So to get around this, to get rid of that noise that's just inherent in the electrodes, you can use a differential amplifier to effectively delete that noise. And this is how it works basically. On one end of the differential amplifier, you'll have one of your signals. On the other hand, you have another signal. If they both have the same voltage offset, which in this case they will because they're on the same human, then you can use a difference amplifier to subtract the difference between those 2 electrodes. And what ends up happening is that you end up subtracting off the common DC offset that is on both of them. So this is just one way to get rid of that extra offset. So I'm calling it an offset, but in practical terms, it's called common mode. The common mode is basically the DC offset noise that is sitting on top of your signal. And in this case, it has to do with the electrodes and their interface with your skin. Okay, a couple of notes here. When you can design this yourself. You can get an op amp, you can get some resistors and connect them like this, and then attach your electrodes, etc. Or you can buy them off the shelf. They have differential amplifiers. There's going to be 2 important characteristics that you're going to have to look at. The first one is that you want the op amp to have very small bias currents. And the reason for that is because you don't want any currents going into your op amp that are from the measurement you're taking, because that'll also reveal itself as noise. The other thing is that you can look at common mode rejection, which is something that uh, you can see on a data sheet for a differential amplifier. So let's get to that. One last thing is you can have another source of common mode or DC offset, not just from the electrodes but also from any other external pickup. So even just being near a power line will that will create some stray capacitances that are connected to you, and you can then have a very large signal that's on both of your electrode measurements. And for those of you that have ever designed an ECG or anything like that, or just played with some of the Spark Fun electrodes that you're given, you'll notice that you have a 60 hertz noise is always impinging on your signal, and that 60 hertz noise comes from the walls and any other equipment that you're standing near. So if you're taking like this person here with stray capacitances, you can model that person as this voltage source EB with some impedance ZS, and you'll have some capacitances that are connected to your power line, and that's how they're coupled to you as a person. And so that signal will be then amplified when you're doing any kind of processing. So you're going to use a differential amplifier, like I told you before, to get rid of that common mode. So like if from this electrode or from this stray capacitance you're measuring some signal, from the other electrode you're measuring some other signal, while they both have this common mode voltage on sitting on top of them, when you do the difference amplifier, it actually subtracts off that same signal, and then you're left with just the ECG signal that you're left that was hiding underneath that noise. Okay, so if you are designing an instrumentation or a differential amplifier, this is something you have to consider when you're looking at a data sheet. So let's say you're looking at the AD620 as a amplifier. Well, so we know from an ideal op amp that the output voltage, when it's an open loop configuration, that you have this open loop gain times the difference of the non-inverting terminal minus the inverting terminal. So any difference across the op amp will get amplified by G open loop, and G open loop is very large, right? But in all practicality, for real op amps, V out, again, an open loop configuration is equal to G difference, so this differential gain times V plus minus V minus, so that's the non-inverting minus the inverting, plus 1/2 G summation, which is another open loop gain, times again the difference of the voltage at the non-inverting and the inverting. In an ideal world, if you want the op amp to be just like an ideal op amp, G sum would be very small, or at least 0 in this case. That would give you the same equation on top and bottom here. But in all practicality, G sum is actually much smaller than G difference, and so this is the metric you want to look for when looking for an op amp. We want an ideal op amp configuration where G sum is 0, or at least in comparison to G difference, it's much smaller. So that is given to you by the common mode rejection ratio. So this is important. So the common mode rejection ratio is equal to 20 log base 10 of the open loop difference change over the open loop sum change. So given this, these two metrics, you can figure out what the common mode rejection ratio is. Typically, you'll just get the common mode rejection metric. You won't actually get G difference and G sum, but you can actually, measure this if given CMMR. So let's do an example here. So let's say if you want to do a gain of 100, this is not gain of this, then this is saying that your common mode rejection ratio is going to be at least 110 and at most 130 decibels. Alright, so let's say you have 120. Say we're in the middle there, right? So for a common mode rejection ratio of 120, what does that calculate in terms of the relative differences in G difference and G sum? So you just get 120, plug it in over here, divided by 20, and you're going to get 6 equals log base 10 of G difference over G sum. When you work that all out, you'll find that G, in the case of a common mode rejection ratio of 120, you're going to get that G difference is 1,000,000 times bigger than G sum. So obviously that, the higher this number is, the better, because that means you're rejecting more common mode than another op amp that wouldn't. Okay, so another, I guess to further increase the common mode rejection ratio, you can then use what's called an instrumentation amplifier. So this is just basically the same thing as a difference amplifier, except that, and this is the difference amplifier here, but now you're attaching 2 buffers at each ends of the electrodes. So why would you want to attach the buffers? It goes back to the previous discussion I had with you earlier regarding the impedance of the electrodes, right? They're very non-linear and they're very complicated. So the impedance can change the gain of your amplifier. So to get around that, you're going to put buffers here on each end of the electrodes. That way you effectively increase the input impedance to the electrodes, and so you essentially then isolated the electrodes from your difference amplifier. And so just the take-home message here is just that the instrumentation amplifier is just a difference amplifier, which you'll see in this little box, but you'll have some unity gain buffers that are sitting at the electrodes to increase the input impedance. So one thing I forgot to mention at the beginning of this lecture is that I'm assuming you guys all have taken ECU 240 and at least understood to a certain extent, why, the bias currents into the op amp terminals should be 0 and all that stuff. So I'm assuming you know that. If you don't, please brush up just a little bit so you can follow what I'm saying with this part of the lecture. Okay, so now let's go back to the actual ECG scenario we had. So let's say you're given like the right arm and the left arm electrodes, and you're asked to then make an instrument that, once you apply the electrodes to the body, that will allow you to basically measure the voltage difference between those electrodes, right? Remember that the voltage difference is proportional to how parallel my cardiac dipole vector is to that lead connecting those 2 electrodes. So you're going to get those 2 voltages. They have noise on them, but you're going to then pump them to a buffer, which then goes to a differential amplifier. And it turns out, if you do the math, which we'll do in a second here, that the output voltage is equal to some gain times the voltage difference of left arm minus right arm. And that'll give you the voltage that you want to read between 2 electrodes, which then will tell you how proportional or how parallel the electrical activity is to the heart, or I'm sorry, to that lead. So you can actually tune the gain by changing the values of R and R gain, and that'll just basically give you a different gain you can adjust. So you can make this by yourself, again, with the caveat that you pick the appropriate op amps, or you can even buy this as one chip, and you can then just attach a couple of resistors and one gain resistor to basically mess with the gain of your amplifier. Okay, so I think, let me get to the let me get to that here in a second. So this is what I wanted to show you. Alright, so this sheet, it's only 3 pages, and if you hated EC240, then I apologize, but this is just a rehashing of op amps. What I'm doing here is I'm taking the differential amplifier circuitry that we saw, given V1 and V2, what is V out for these resistances and these connectors here. And what I just want to remember is this, is that, you know, when you have negative feedback here, just know that the currents going into the op amp terminals have to be equal to 0, the non-inverting and the inverting, and that because you had negative feedback, the op amp will do whatever it can to make the non-inverting and the inverting terminals the same voltage. Knowing all that, all you got to do is just use node voltage analysis, which is just KCL. Whoopsies. It's just KCL at each of these nodes. So here's a node here, there's a node here, and there's a node right there. And do that analysis, and you'll get essentially this equation here. And if R1 is equal to R4 equal to R3 equal to R2, then it simplifies to just a unity gain difference amplifier. Alright? And if it's not, then it's up here, and you can calculate what that difference is. Okay, now to the instrumentation amplifier. So again, this part here is just a difference amplifier. And this part here are your your unity gain buffers. So again, I'm labeling all the nodes in this circuit. I'm doing KCL, and what I get out is this equation right here, which is the one that you saw in the PowerPoint. So again, I've just derived everything for you, and if I would say that go through it yourself on both of these, because it's fair game for the next quiz in terms of, you know, deriving, etc. So make sure you do that. And if you have any questions, just let me know. But go through it, and it's just KVL and just KCL. Sorry. All right. Let's finish off this lecture here. Let me. Okay. So that's how we got this specific equation here. Okay. So we've talked about different methods to get rid of common mode. There is one more way or additional thing you can do to eliminate common mode, and that's basically what's called the right leg drive. That's down here. So what you can do is you can get the left arm and right arm voltages, and again they're going to have some common mode signal that's basically acting as noise. You're going to get your instrumentation amplifier, and you're going to tap into where you can actually measure the common mode signal. You're going to get that signal. You're going to then apply it onto a inverting amplifier, and you're going to invert the common mode signal, and you're going to drive that signal back to the right leg. So what you're basically doing is you're creating a negative voltage of that common mode and putting it back into the person. Now the inverting amplifier allows you to attenuate that signal a little bit so that you're not zapping the person, but that's another way to eliminate it. So what you're actually doing is you're pumping back in charge to effectively eliminate any charges or any other noise that's impinging on these two electrodes here. And it actually works fairly well. So let me just summarize again how to eliminate common mode. To eliminate common mode, you would get a really good op amp that has good common mode rejection ratio. The other way is that you use silver chloride electrodes because they have a small amount of voltage difference just from their inherent properties, and using a difference amplifier to get rid of that common mode. Alright, so some additional circuitry you can do. You have your instrumentation amplifier. You're going to need to do some filtering. Remember that I told you that you do have, even if you still get rid of the common mode, you might still have some other frequency, what should I say is different frequency noise. So you can put a high pass and a low pass filter to essentially make a band pass filter, to pass only the frequencies that you're interested in for the ECG, and then you can even amplify that signal, because once you've run it through the filter, you might get some attenuation. So then you would amplify it again to get back the signal that you want in terms of the magnitude. So all of this is what we would consider to be front end circuitry for the ECG. All right, so here are two examples of some bioinstrumentation systems that they're older, but also a little more current as well. So one of the first examples is a pacemaker, and we'll actually see this again in the tissue stimulation lecture. So the way a pacemaker works is you have some electronics that are sitting in what's called a can, and then you have some electrodes, some leads that have electrodes at the very tip of the leads. And the way it works is you have this can, which has the battery, and you have this lead that then goes into the vasculature of a person. And so I forgot to mention that a person that has an arrhythmia, they typically have some problems with their the conduction pathways of their heart. So you have to stimulate a specific portions of the heart to resynchronize their heartbeat. So to do that, you'd have the external stimulator hardware in a can that's underneath the skin. You would then get the lead, and you would put it through the vasculature and run it into the area where you want to stimulate. At the very edge of this lead, there's going to be some electrodes for stimulation. Now, you can't just stimulate willy-nilly. You actually have to measure the ECG of the person. So within these leads, you also have an ECG sensor that measures the local ECGs in the heart. So this was actually Earl Bocken's first design. It was a transistor-based pacemaker. It was one of the smallest pacemakers at that time. So kind of a background behind this kind of endeavor. When hospitals at this time were, needing pacemakers, the pacemakers were actually the size of like a refrigerator, and you'd have to actually plug into the wall outlet to power these devices. And it turns out, I forgot what hospital it was, but the power went out, and a lot of patients died because the power went out in the hospital, and there was some patients that were on these pacemakers. And so Earl Bocken, he's the founder of Medtronic. He actually designed a battery-powered transistor-based pacemaker that didn't have to be hooked up to the wall outlets. So from then on, it's evolved to these what are called like implantable pacemakers. They've even gone a lot smaller. They've gone to the point of like what are called leadless pacemakers, where you don't have this can and you don't have this lead that's going into the vasculature. Here's a kind of a block diagram of what you have to do. So to sense the ECG, you have to be able to sense a specific part of the ECG wave. You amplify it, you filter it, and you can then have some threshold circuitry to measure the threshold, and then from there you can then apply some voltage to the tissue, and that's how these work generally. But this is just an example again of you have to design electrodes that can be implanted in a person's body and relatively small in diameter. Another application of bioinstrumentation is the kind of marrying of imaging and ECG. So there's a company located in Irwindale. They're part of Johnson & Johnson. They have designed this system called the Carto 3, and it's basically this here. But what it really is you have this instrument that connects to catheters. So catheters are very long tubes that can be inserted in the vasculature, and these catheters are they're very unique. So they have some three-dimensional positioning within the catheter, so you're able to actually, when you implant this in a person and you maneuver the catheter through their vasculature, you can actually locate where it is in the person. And so that allows you to, for like 3D localization of the catheter tip. At the tip of the catheter, you also have some electrodes that can measure the ECG of the heart. And so if you have this catheter that's going inside of the heart, you can measure the local ECG of that heart. So they actually merge it with MRI imaging and CT scanning so that they're able to get some anatomical images of the heart, as you can see like in the gray. And on top of that, they superimpose ECG data that they're measuring. So because they have a maneuverable catheter, they're able to measure the ECG in different positions and basically map out the ECG mapping of the heart on top of the anatomical image they get. And that's nice because, once they get these images, if you have an issue with, like arrhythmias, you can basically figure out where exactly you have to apply your pacemaker leads, or where you have to basically ablate or burn tissue. So very interesting. This is kind of more state-of-the-art technology for arrhythmias. Okay. So I think that ends this lecture here. So next week we're gonna have a Boston Scientific talk. They'll be talking about stimulators, and we'll also get a little bit into some biomedical sensors. We'll get into some electrochemical sensors, sensor fabrication, and potentiostats, and that kind of stuff next class. Thank you for listening, and I'll see you all next week.